Thank you. Glad you're here.
All right, hang on just a second. All right, I'm John Everett Jr., Vice President of Geological Jackson Hole, and also like to welcome you here this evening. It's my pleasure to introduce our speaker tonight, Dr. Robert Killing, Scientist Emeritus with the United States Geological Survey, Volcano Center. In 2004, Bob officially retired after a 42-year career as a volcanologist with the USGS, but certainly he continues his studies of volcanoes, volcanics around the world, occasionally consulting with work on volcanic hazards. He's the author of 8 books about volcanoes and earth processes, as well as numerous technical papers. He has advised foreign governments, studied volcanoes across the globe, and managed various scientific teams and organizations within the United States Geological Survey. During the reawakening and eruption of Mount St. Helens in 1980, he was in charge of USGS studies, deeply involved in the USGS handling of that event. In recent decades, he has also been actively involved in educational outreach and co-authored the USGS's all-time best-selling map, This Dynamic Planet, which is a world map of plate tectonics, specifically intended as a teaching tool. He's a member, or pleased to say, of the Geologists of Jackson Hole. He's actually a board member for us. He's a regular visitor to the Valley, where he and his wife Susan, who is here, spend part of each summer with their daughter Karen Coleman, who is also here, who is VP of the Jackson Community Foundation, and their lovely family. So without further ado, I'd like to ask you to join me in welcoming Dr. Robert Killing.
Okay, now I turn on the button.
Yep, you're good.
All right.
I hope.
Testing, testing. It's good? Okay, great. Well, it's always a pleasure for me to come here to talk to this group about one of my favorite topics, volcanoes. And if everything works, I hope to give you some highlights of a very interesting volcanic eruption at Kilauea Volcano last year. And so I'll be showing a lot of gaudy pictures, probably, and some video clips, and everything all works. And then I'm going to try to leave lots of time for questions and answers afterwards. Now, probably half of you in the audience here were probably involved with those field trips we made to Hawaii in 2016 and 2017. And it was a great pleasure for me and Rick Hazlitt at that time to show you guys around. So in the course of the talk tonight, you'll probably see some pictures of places you saw before on the field trips. But it might look a little different now than just when you saw them. So anyway, so don't be surprised. Now let's see if this thing works. Oh, bingo. Okay, well, I'm going to try to cover these broad topics in the time that I have. And basically in the introduction, why we have volcanism in Hawaii, a summary of the eruption last year, and some of the impacts of that eruption, and what new things have we learned about it from that eruption, and what's actually happening now at Kilauea, which I think you might find also interesting. Now, I think all of you people know here that we have volcanoes in Hawaii because of the Hawaiian hotspot. See if this thing works. Hey, it does work. Okay. And the over 70 million plus years or so, the Pacific tectonic plate has traveled over this hot spot, leaving a trail of volcanoes behind it, something that we call the Hawaiian Ridge Emperor Seamount Chain, which is this thing right here. Now, the island of Hawaii itself, the Big Island, is composed of 5 volcanoes, and shown on the left here. And all of the eruptions that have taken place at these volcanoes occur either at the summit calderas or along rift zones, shown in pink in the left-hand side. And the topic tonight, we're going to talk about the lower East Rift Zone. Oops, there we go. right here, and something about the Kilauea summit caldera as well. And here's a closer up of the map showing where these places are. You've got the caldera, you got the Pu'u O'o eruption, which was a very, very long eruption that lasted from 1983 to 2018. And then the eruption last year that started in May, early May last year. And I'll talk about this other map a little bit later in the talk. Okay, here's a cartoon by one of my colleagues at the USGS showing how the whole system works at Kilauea. We have a shallow magma reservoir, which is something on the order of 2 to 3 miles below the ground surface. And that's the holding tank for the molten rock or magma that comes up from the mantle. And it's stored there until it's erupted, either at the summit or it's intruded along one of the rift zones to erupt, to form a rift eruption. And this diagram here shows pretty well what was happening last year. Up until May 2018, we were having simultaneous eruptions with a lava lake here in Halemaumau and at Pu'u O'o on the East Rift Zone. And then things started to happen, and I'll try to go through that this evening with you. Now, here's a listing of all or some of the major impacts of that eruption and the significance of those impacts. And I'll cover very briefly some of these items, and I won't list them down the road here. But let me just say that the eruption last summer, into the summer, was the largest lower East Rift Zone eruption in the past 2,000 years. 200, I'm sorry, not 2,000. And it was characterized by very high eruption rates and very high gas emissions, principally carbon dioxide. And even during that eruption, one of the fissures erupted some andesite, which is a very weird rock for Hawaii. That doesn't happen there. You know, we mostly get basalts in Hawaii, like 99.999%. And so that happened. That was kind of strange. But overall, about 1 billion cubic yards of lava were erupted. And at the same time, the summit of Kilauea was collapsing in about the same volume. So things were shifting between the summit and the rift zone. And lots of new land was created by the lava. And so some very new properties for people to consider on the coast. Which, of course, any new land created on the coast belongs to the state of Hawaii, even though if your lot was adjacent to it. But that's another story sometime. Okay. It was probably one of the most disruptive and destructive eruptions in the past 200 years. Nearly 2,000 people had to be evacuated from their homes and subdivisions in the Puna district, which is sort of downslope from the East Rift Zone. Over 700 houses were destroyed, 30 miles of roads covered. But at the same time, because we had this sort of interaction between the Rift Zone and the summit, there was a potential for serious, larger, explosive eruptions at the summit. And that ultimately caused the national park to close, and actually the evacuation of the HVO building, which many of you visited on your field trips. And that building is still evacuated, even as I speak now. But one of the interesting things, it was the first use by HVO and the USGS of drones in eruption monitoring. You know, we use the helicopters and ground-based, satellites and all kinds of things, but this was the first eruption where we seriously started using drones to help us get data that we need. And as it turned out, because of all of these combinations of techniques, the eruption last summer is probably going to be one of the best monitored eruptions ever to date. And my colleagues there at HVO and USGS are going to have lots of very important studies coming out in the years to come. There's so much data from this now, it'll take them years to analyze it. Okay, so what was kind of leading up to the eruption? There was actually kind of steady state activity, both at Pu'u O'o and the caldera, through 2017 and into the first part of 2018, and then things started to change, started ramping up as the whole system got kind of plugged up and became pressurized, so that not only was the summit inflating from the pressure of the incoming magma, but also the rift zone itself. So the whole system was gorged. And as a consequence, the active lava lake that was in Halemaumau had started to rise. And those of you who were there before, you saw it, but it was much lower level and was much smaller at that time in 2017. But this is now starting to rise. And ultimately, by late April, the lava lake started spilling out to the rest of the crater floor of Halemaumau. And that was rather spectacular, and it was well documented. And then things started to happen in the rift zone. Pu'u O'o crater collapsed by magma moving farther down the rift zone and leaving a void, basically. So it collapsed on April 30th, and this is the big dust plume that rose from that collapse. Here's a picture of Pu'u O'o before that collapse. That's a picture on April 23rd. And you can see here, there's still an active lava pond, active here, and the crater there. And I want to point out these two oval areas are points of reference when we go to the next slide. You'll see what Pu'u O'o looked like after the collapse. Okay, so all the active lava is gone, a huge, much deeper crater now, and you can see for reference the two places that were not greatly affected. But a whole new crater, much deeper and wider. Now, because of this intrusion from the collapse of Pu'u O'o into the lower rift zone, there were a lot of earthquakes started to happen at that point as the magma was cracking through. And this slide here shows the zone where this increased seismicity was happening between April 30th and May 2nd. So the system was just pumping into the lower rift zone. And then on May 3rd, first of the 24 fissures opened up in the middle of a subdivision called Leilani Estates. And you can see right in the middle there, it looked pretty small, looked fairly harmless, very small. But this was going to be the first of the largest historical lower rift zone eruption. And here's a flow map of that. So in the space of about the first week or so, after that first fissure, there were new fissures formed. So you had a total of 14 fissures that opened up within the first week in kind of an in echelon parallel fashion you see in the map here. But still, even at this time, the amount of lava put out was still relatively small. They were really disruptive to the subdivision, to be sure. That ultimately 10 more fissures opened up in May in the next couple of weeks. But fissure 8, which would be the dominant one in the story later on, really was the one that pumped out the most lava to destroy the areas and to cover the land. And we'll talk more about this a little bit later on. Okay, now we're going to show us a video clip. If it works, let's hope it does. Okay. Here it is. Here you are. You have a house in the subdivision. You look out your door and what is this thing? And this is a fairly typical picture of a lava flow on flat terrain. On steeper terrain, it's a little faster, more bulldozing. But something like this is pretty typical for flat terrain. Now, if everything works, by clicking this, I should go to the next slide. Yeah, okay. Come on. Okay. Here are more scenes of what's going on in the subdivision. Now, this is fairly common in many, many Hawaiian eruptions. You get methane gas, which is generated from the decomposition of the vegetation and soil by the heat of the advancing lava. So you get these flames playing along until it's covered up by the lava. Okay, let's see now. We can go to the next slide. Come on. Bingo. Okay. By the way, all these video clips are available on the HVO website, so you can download them. Okay, so here's a view from the chopper of Fissure 8, which is or was the dominant vent at that time. And here's what it looked like on the ground, sending up lava fountains, 200 to 300 feet high. And of course, this is feeding flows, which is wiping out the subdivisions and land down slope. Well, so far so good. These things are working. Okay, here's a little closer up view, a photo of some of the lava fountains. Well, this shows some of the 700 houses being destroyed with advancing lava flows, and people were evacuated. They were advised to leave, but you can't move your houses with you, so you just. Now, as it turned out, there were no fatalities from this eruption. Everything was very highly destructive to property, and only one person got injured. So it was damaged from the lava flows. I draw your attention to that one picture there showing, some of our cars are not all metal, and parts of it melted just from the heat of the lava nearby, and ultimately got covered up too. Now, as I emphasized earlier on, this eruption had very high rates of output. The lava came out at a very high rate per unit time. And here's an aerial picture view of a very massive lava flow fed by Fissure 8. And here's one of the places, in addition to helicopter flights and airplanes and satellite data and ground-based data, we started using drones to make very, very detailed studies of lava dynamics. And from the drone data, we were able to actually measure the velocity of that one stream, lava stream, at mid-channel there was traveling about 21 miles per hour. Now that's in the center of it. Of course, at the edges it would be slower because of the drag. So that's a very fast-moving flow and highly hazardous if you're in its path. Now, from this kind of data and other data and some modeling data, you can actually get the eruption rate. And for after May 18th, the 2018 eruption had a very high rate of about 130 cubic meters per second of output at the vent, which is phenomenal. When compared to previous eruptions in the rift zone in 1955 and 1960, was only 30 to 40. So it was 3 to 4 times more vigorous in terms of output than previous eruptions.
Bob, what kind of sensor did you have on the drone?
Thermal cameras. That's a thermal image there. But I'll talk about that. We also have gas sensors and things on them too. We try to maximize it. And by May 19th, the first lavas actually started to enter the ocean here. And this is near where some of us not last year, 2 years ago now, actually visited and actually took a boat trip from there once.
Where did we head out?
It was near Opihikau, actually near Pu'u O'o, sorry. In fact, I'll show some pictures of that. But anyway, the Big Island has a geothermal plant. It's the only operating one in the state of Hawaii. And it produces something like 38 megawatts of electricity, which helps the cause on the Big Island, which has the highest utility rates in the country. And here's the plant. Puna GeoVenture was totally surrounded by lava, and parts of it were covered up and buried, including some wellheads, and anyway, it caused damage. So it had to be shut down, basically. And it's still shut down even now, although they're hoping to reopen it late at the end of this year or possibly early next year. They've got roads back to it now. They're actually repairing things and doing some re-drilling and so on. Okay. I'm now going to show some really good videos of lava entry into the ocean at Kapoho Bay. You can see the lava flows coming into the ocean, and part of it, it's already cooled on the left there. There's another view of that. And then, by the next day, the entire bay was filled. And of course, any houses that were there got covered up, of course, and it spread. Here's another view showing a very vigorous flow in late July. And you can see the vent, Fissure 8, and then in the far distance in the horizon, it's entering the ocean there about more than 10 miles away. Here's the place. Pohoiki boat ramp got caught up in some of this ocean entry of lava. And you can see that the place where we caught the boat from, the boat ramp, now is totally isolated. There's a new black sand beach, and there's some new 2018 lava. And there are discussions going on whether to try to resurrect that boat ramp or not by building new roads and so on and so forth. Now, at the time when some of you visited, the ocean entry was not quite as spectacular as this. Here we were, it's a picture showing the ocean entry covering about a mile across. And of course, you know, for the lava boat tours, for tourists, this was an incredible time for people to see this kind of action. And here I'm going to show a video clip of one of these tours in late May. It's not a garden hose, folks. It's a lava hose. Okay, now note as you're watching this, the little black specks and chunks flying around. Well, those are explosive debris from the 2,000-degree lava hitting the cold ocean water. So there's a lot of explosive activity as well. Now, you see how close these people got. Now, this might have been telephoto or whatever, but still, it was pretty darn close. But then, a boat, like in July, actually got a little too close, or the explosion got a little too powerful, and a lot of lava bombs and explosive debris, including one that came through the roof of the boat. And so obviously the tourists probably got more than he bargained for. But luckily, there were only 23 injuries, and only 4 had to actually go to the hospital for treatment. but they were all minor, and the rest were treated at the site, or not treated at all. So there is a hazard to this. You know, lava entering the ocean does, yes?
Was that our boat tour company?
Yes, it's the same company that we took. But that was then. See, that was 2017, and this is 2018. Anyway, it's actually, my family also took a tour during this eruption last year in the same company. But luckily, nothing happened to us.
Were they able to motor back on their own power?
Yes, they did. Yeah. Okay, so to summarize, here's a map showing the whole flow field from the 2018 lower rift eruption, and the Pu'u O'o, the Azekeo Park is where we visited. And you can show the positions of the 24 fissures and also the new land that was formed. You can see the former shoreline is that white dashed line there. So that much bigger now for the Big Island. Okay, now so far I've concentrated on what's going on in the rift zone. Now we're going to turn our attention now to what was going on at the caldera, at the summit. Interesting things were going on there too. Basically, the main trend was a very sharp deflation that started to happen once the magma started to move downrift. Then the summit starts to collapse or deflate, as we say, and that was sort of facilitated by a magnitude 6.9 earthquake that happened on the south flank of Kilauea that involved about 5 meters of slip. And which basically then, that was kind of just juiced up the whole system by opening the rift zone wider by meters. And so that just accelerated the deflation to feed the very, very vigorous lava output in the rift zone, downrift. But at the summit, it started leaving basically holes and cavities, leading to collapses and explosions just from the pressure surges coming up through from the collapses. And shown there, the little sort of jagged lines on the red are a series of what we call collapse explosion events. It involves an explosion and collapse, and then a recovery of the system, then another one. And this went on for like 62 times for the next several months. Now, this is the Halemaumau lava lake, which was active. Remember, it was overflowing in late April. But with that sudden draining and deflation, that here by May 6th, it had dropped way down because the magma was flowing out in the rift zone. And then by May 10th, it was totally gone. You couldn't see it anymore. It had disappeared at a depth of 320 meters. So it really dropped. The bottom dropped out. And as the bottom dropped out, the crater is very unstable, so you have huge rock falls. And here's a very large rock fall falling into and causing this plume on May 9th. And then on May 16th, there was the first of these series of collapse explosion events over the next 2 months. And here shows one of them on May 16th. And these clouds would get up to, on the order of 20,000 feet, 30,000 feet. It all varied from event to event. Now, the last time when something like that happened at Kilauea Summit was in 1924, one of the few explosive eruptions that happened in historical time at Kilauea. And at that time, it triggered a series of summit explosions that lasted for about 2 weeks. But it was powerful enough to actually throw out big blocks like this with an impact crater when it fell, and some people for size. That was 1924. And during the 2018 eruption, similar blocks were thrown out, but not quite so large. But there were blocks that got thrown out. And not all of them, but some of them. Here's one on 27th of May, which is one of the larger ones. Okay, now you have some people interested in the eruption. Okay, you see the people watching the plume back of these golfers? And these golfers, hey, I'm playing golf here, you know, I paid for my fees here or whatever, you know. Well, anyway, so here's a summary of those 62 events, and they're very, very nicely recorded, very prominent. You know, you can see the earthquakes per hour shown in blue, and then the tilt in the jagged curve showing every time it would collapse. You know, of course, the summit would deflate, then it would recover, and then it would deflate again with each pulse. And as I pointed out before, the May 4th earthquake helped the whole process going by having this 5-meter movement slippage toward the sea and opening up the rift zone.
Now what's,
Oops, sorry, you want to go back?
Is tilt something, is
Oh.
actual tilt or is it just up and down?
Okay, I probably should explain that. Tilt is a measure of the slope of the volcano. And there are tilt meters for this. There's various kinds of instruments that measure the tilt. And it's and so that actually it's like blowing up a balloon. You blow it up and the slope gets steeper and steeper and steeper. But it can be measured in microradians, okay? 1/1,000,000th of a radian. So it's equivalent to 1 microradian is equivalent to if you have a mile-long 2x4 and you put 1 nickel under it.
Okay.
The systems can measure that kind of precision.
Tilt measured from one point to another point?
Well, it depends. If you have a tilt meter, it's that point itself.
Right there, sure.
But then if you actually have several points, GPS, I'm losing my voice here, you can actually calculate the tilt.
So where the tilt goes from plus to minus, does that mean that it goes from being a dome to being a pit?
No. I mean, yeah. Well, actually, at the summit, it was incremental. So each down drop would give you one of these pulses, and then it would recover slightly, then it would drop again. So that's what these jagged curves are. And anyway, this went on until August 2nd, when the whole thing stopped, at least in terms of the collapses. And you can see see how the flat curve there, I mean, there's none of this stuff anymore. It's very, very normal behavior for the volcano. Okay, now here's a good example of various data that can just really nail this thing down. And this is going to be studied and analyzed in great detail later on. Pardon me. So you got tilt measurements, you know, the slopes of the volcano changing. Then you got earthquakes per hour. And then you got GPS measurements for horizontal and vertical changes. And then you have something called RSAM, and that's a total seismic energy release regardless of the location of the earthquake, just the whole shaking of the system. Okay, here's another example of that. And on August 2nd, you can see how everything is going up and down from the collapses that are repeated. And then finally, after August 2nd, things kind of really quiet down, and the eruption starts to die down, downrift as well. Okay, here's kind of a conceptual model of what the H-field people think. You have a block conduit, and it's, you know, magma starting to drain, but it's stable for the moment. Then as the magma drains, as the rate of magma draining increases, the stresses on the faults then increase in producing earthquake swarms on ring faults around the crater. Then finally, the piston collapses from its own weight, and that's where you get one of these big drops, and then it rebuilds up the same way. And these happen on a frequency of about tens of hours to days, so very regular. Okay, now I'm going to show us some time-lapse views of these collapses or the changes in the Halemaumau Crater. And here is the first day is April 14th, and you still see the lava lake active, putting out a plume. And I'm going to start this thing now, and watch the little tree there on the right That's kind of your point of reference. All of the frames, it's the same view, but you'll see how the land is just dropping out in front of your eyes. Okay, now this is May. So you now see some of these collapse events. June, July. Did you see that whole caldera just dropping? Now, I mean, that is geology in action, folks. I mean, we talk about erosion rates and that things happening over thousands and millions of years. But you saw in 2 months' time there what happened to that crater.
Did you run it again?
Well, I could. Okay, I'm going to see if I can back up. Well, here, let's try it again.
I was watching the tree.
Well, I can't seem to get this thing to go, John, to go run it again.
The back button won't work on it?
No. Oh, okay. Well, all right. All right, I'm going to run it again one more time.
Okay.
It's pretty short.
Oh, the lava dropping.
Just the wall just fell right in.
Oh. Look at that. Oh.
Okay.
How close did it creep up to the observatory?
Well, you still can go to the observatory. It has not fallen in.
But a lot of the land out to the crater is gone, right?
Yeah, well, in fact, that was part of the rationale with these collapse events and also the possibility of the explosions that the building was evacuated. Now, throughout the whole process, HVO managed to keep the monitoring going, and I'll talk a little bit about this later on.
Is the hotel still open or not?
It's open again now, but it was closed during the eruption. Okay, now here's just kind of the absolute before and after. Here's before the whole sequence of collapses on April 14th, then after. You can just look at the size of that crater and how much it's dropped vertically as well.
What's the name of that crater again?
Halemaumau. It's within the larger Kilauea caldera.
The trail system that we walked around up there, that must be big time changed, right?
Yes, yes, it has changed, right? Okay, now here's just again a different perspective. Okay, these are just in the topography, a view from above. You can see in 2009, the active lava lake was that part shown there in red. And then after the eruption last summer, you can see how the whole topography has changed. And there's a new fault scarp there, as indicated, that's about 460 feet high. And here's another way of looking at it. The blue line is April 2018. And after the collapse events, what it looked like in August 2018. And the Empire State Building is given as a reference for scale.
Well, Bob, you were measured, the data shows micro radians. Now,
Yeah?
This is giga radians, right?
No?
It's just
No.
elevation.
No, here we're just talking about meters in elevation. Okay, now this is an actual cross section. Nothing more, nothing less. It's a cross section showing the vertical change in the profiles.
When that dropped down, what was the magnitude, earthquake magnitude?
Okay, I was going to get to that in a minute here, but each collapse event was equivalent in seismic energy to a magnitude 5 point plus, 5.3 or 5.4. So these were seismically very, very energetic. Okay, so looking back when this whole thing is done, as I mentioned earlier, this was one of the largest collapse events in the past 200 years. And this shows a comparison of previous collapse volumes. The red points are Kilauea. And as you can see here, there's the 2018, and way up here in terms of the volume collapse. And then the blue and the purples are some other worldwide events. Piton de la Fournaise in Reunion Island, Tobacek is in Kamchatka, Miyakejima is Japan, and Fernandina is Galapagos, and Barbarbunga is Iceland. So in this particular period of time, since 1800, only two events around the world were larger than what happened at Kilauea last year. And here's an aerial view again. Now this shows where I used to work and where a lot of you visited on the field trips. And you can see that the rationale, you can see the concentric fractures going around, and the building itself was heavily damaged and cracked, and so it was a very wise decision to evacuate and work elsewhere.
So the white material is ash?
Ash, that's the ash from all these big, yep.
Can you see that fault scarp on that picture?
Pardon? Let's go back.
Scarp visible on that picture?
Yeah, you see the downdraft?
Oh, yeah.
Yeah.
Coming right at you.
Okay, now, I pointed out earlier on that this eruption was also one of the highest gas producers. In terms of the gas emission rate, it was huge. And on this slide here is shown that the data for SO2, and part of this is obtained by conventional land-based and air-based techniques, but also using some drones later. The green and the orange dots down here show what I was doing before the eruption started in early May. And that ranges in purple are the rates of gas emission during the time of the lower East Rift Zone eruption. You can see it's way, way higher, orders of magnitude higher than under normal situations. And now,
What is the T per day?
tons per day.
Holy crap.
Tons per day.
Now, were you getting CO2 out of it as well?
Yes.
Okay.
But I'm only showing the SO2 here. But you can see that after the eruptions was over, then you go back down to the very normal levels of gas emission again, right? Pretty close to zero. And this is interesting. This shows the eruption last year had the largest annual carbon dioxide release since measurements have been made in the 1970s. You can see during that steady state eruption with Pu'u O'o in 1983 and the Summit Lava Lake kicked it up. And then you look at what happened last year, and that it is huge in terms of gas output. Now this is a little interesting sidelight that I didn't realize until I saw this photo. Because of the high gas emission rate, and with the prevailing winds, the downwind side from the lava flows and the vent got killed. It was very highly toxic gases. But look on the upwind side, it's very little affected. It's still tropical green. So that shows that the effect of the toxic gases. Okay, I mentioned that it was the first time we started using drones to try to make some of these gas measurements, and there's a picture of the drone being programmed and everything, and I don't know the details of this, but this is the flight path of the drone as it sampled and measured the gases to get a estimated emission rate.
What's the difference between the green and the red there? Do you know?
I don't know. Okay, I don't know that for sure, but my guess, John, would be that the red are areas of higher emission.
Yeah.
Okay, so what they're actually mapping out, that one there was probably a fumero, that's my guess, and by coordinating that with other information, you can say, oh yeah, that's the highest emission is coming out of those areas. And well, in addition to all the scientific work that the HVO staff had to do, and HVO, by the way, had a lot of help from other USGS folks at other volcano observatories, the Cascades Volcano Observatory, the Alaska Volcano Observatory, the Yellowstone Volcano Observatory. Everyone had to help because these guys were swamped. They were just working like crazy during this time. It was very crazy. In addition to the scientific work, then of course all of the public interaction had to go on between the civil defense people and FEMA and the general public. That took a lot of time too. So there were many, many meetings between the scientists and people affected, and that took a lot of time. And as I mentioned before, HVO itself at the Jagged Museum was damaged, heavily damaged from the earthquake activity, and it shows the asphalt here too. And you can see some of the cracks going through the viewing area, and that was the reason for the park to close the visitor areas and for HVO have people working elsewhere, but not in that building. And here's a picture showing some of our people working out of the geology classroom at the University of Hawaii Hilo campus starting in May. And luckily we could do this because it was vacation. It was a ready place to work. And they were very, very, very helpful. Okay, so now what's happening at Kilauea? No live lava has been seen since 5th of September last year. So that is kind of officially the end of the 2018 eruption. And the current monitoring data show no significant changes going on with Kilauea. Sort of routine, modest deflations and inflations, but nothing unusual, kind of steady state. And the sulfur dioxide emission rate are very, very low at the summit and below the detection limits at Pu'u O'o and lower East Drift Zone. But what is interesting, has caught the attention of the scientists now, is the appearance of ponded water at the bottom of Halemaumau, which has never been seen before until this eruption. And here you see the view of Halemaumau, and at the very bottom of it, with a thermal camera, they actually detected ponded water at a minimum temperature of 70 degrees centigrade or so. And on the right there, you see a close-up photo of that little ponded water. And like a lot of water in volcanic craters, it's kind of greenish, yellowish, because it's you know, it contains compounds that color the water. So it's not pure water by any means. So what's the reason for this? Oh, here's another view of that. Okay, so that was first noticed in late July of this year now, okay? Not last year, I jumped a year on you here. This is happening now. This is real hot stuff. And so here's a picture on August 7th, August 23rd. See, you see the level is rising. You can pick out some of the same rocks for reference and how the level has come up. So it's coming up. Oh, wait, let's back up. And okay, so this was very curious. This has never been seen before. So what's the source of the water? Is it just rainwater filling in the hole? Or is it groundwater rising up again and recovering after all the collapses? And the current thinking seems to be that there's no fluctuation variations with rainfall. With rainfall, you might actually see it going up and down depending on your rainfall. They don't see that. It's a steady rise. And so the thinking is that this is the groundwater level of the groundwater system recovering after the massive collapses. And once you get away from Kilauea, from this area, there's a drill hole that was drilled back in the 70s. It shows the water level in that drill hole to be about 70 meters higher than the level of this. So the thinking is that this will probably continue to rise until it reaches equilibrium again with the overall water table. So that's the thinking. That's the thinking. I think I'm going to make it on time. I'm going to leave time for some questions. And then finally, just leave you a little tantalizing here. Okay, I mentioned it was a huge eruption. About 1 billion cubic yards were erupted. And that little trivial fact there, that's enough to cover 2 lanes of Interstate 90 from Boston to Seattle with lava about 70 feet deep. That's a lot of lava, folks. Right?
Probably wear pretty well, too.
And that's the end. I hope there'll be lots of questions, and I'll try to answer them. But I have to thank my HVL colleagues and the HVL website. Virtually all of the stuff shown to you was available if you poked around enough on the website to get it all out, which I tried very hard to do. And with that, I'll stop and answer questions.
Any thoughts about the recharge of the lava reservoir from the mantle from below?
Yes, of course, that'll be something we're looking for very precisely. But so far, from the monitoring data, meaning by that the tilt measurements that are still being made, as the magma recharges, we ought to start reinflating everything again and bringing it back up. And so far, we've seen very modest reinflation, but nothing significant yet. So at the moment, it does not seem like there's a sudden recharge of magma coming into the system. It'll happen, probably. A very similar thing happened in 1975 when we had a larger earthquake, a 7.2 magnitude earthquake, and it took quite a few years before the whole system kind of got recovered and reinflated to kind of a normal pattern.
So those tilt meters will be one of your basic
tilt meters,
indications of that.
GPS, and also the gas sensing. You know, as the magma comes in, we ought to get higher gas emissions too. So we look at everything, all the possible data, the earthquake data, the ground deformation data, and the gas data, to give us a coherent picture of whether the whole system is rebuilding again or not. And it probably will. I mean, it's not a dead system, but for the moment it got the heck kicked out of it. And
You had a volume of material that sank out of the crater.
Yeah.
And a volume of lava. How did those two numbers?
okay, I should have probably said that they're about equivalent, as it turns out. Now, it's kind of pretty hard to get real hard numbers on them, but looking at the volume of the collapse and the volume of the lava erupted, they're kind of equal. And the thinking is that there's a hydraulic connection between the two, that as the molten material moved down the rift zone, it was erupted, and the summit collapsed, about comparable volumes were involved. So there's kind of a hydraulic connection between the summit and the rift zone, which we've always known, but this proves it very nicely.
Well, the plumbing for the other 4 volcanoes, do they interact with the plumbing on this one?
That's a great question. Each volcano, we believe, is independent. Now, first of all, the other 3 volcanoes have been long dormant. You know, of the 5 volcanoes, Kohala, the oldest one, probably last erupted 600,000 years ago or something. And then Mauna Kea last erupted about 3,000-4,000 years ago. Hualalai last erupted in 1801. And Mauna Loa, which last erupted in 1984. And Kilauea has been the most active. So, but even between the 2 currently active volcanoes, Mauna Loa and Kilauea, these are the 2 that are active. And also the new submarine one, Loihi, which is also erupting. From all the data we have, they behaved independently and differently. Now, ultimately, since we're tapping the same hotspot, the hotspot is feeding material up, and somehow must bifurcate, sending magma stream to either Kilauea or Mauna Loa, and then there's some kind of a shunt valve in there that must work.
So some deep fissures could happen.
With the deep fissure or the deep hotspot, the source of the magma is fixed. It's still coming up as the plate moves over it. And the thinking is that, well, not the thinking, we know when Kilauea is frequently active, Mauna Loa is not, and vice versa. So they kind of turn off and on, depending on which one's going.
Yeah, CO2 The total CO2 emissions from that event, how does that scale compared to worldwide CO2 emissions? Can you repeat the question, Bob?
Yeah, the question was, how does the CO2 emission from this eruption compare with worldwide emission of CO2? And I don't know a good answer for that because I didn't really dig into the CO2 data, but this is a question that's been asked a whole lot. A lot of the people say, you know, why worry about climate change and greenhouse gases when volcanoes can put out a lot more? Studies that have been done worldwide now by volcanologists that show that the total global volcanic output of CO2 is much less than man-made CO2. Now, that, you know, that's what they say. That's not my specialty, but that's...
Bob, you got a question? Can you talk about the data collection from the clinometers and the GPS? You've got tilt in microradians. What's the resolution on the GPS? Vertical drop? Obviously, if you can measure a microradian.
For GPS measurements, if it's well controlled, you're talking millimeters scale. Oh yeah.
1 or 2 or 3 millimeters.
Oh yeah, yeah, and or up to centimeters in the worst condition if it's not well controlled.
Depending how long you're.
Yeah.
But the clinometer microradians, you know, it's very small.
It's very small.
So those are out far away from the cone, the crater, and they're on the sides, and it's looking at the sides puffing, I guess you'd call it.
That's right. Actually, it's not a single instrument. There's a network of instruments, and at different points on the slope of the volcano, you can actually see the tilts will not be as great as those that are, you know,
soft spot bulges out.
Right. Let's see. Back there. Hi.
So if you were to step back for our benefit, what was it, how would you characterize the cause of this? Was it the Pu'u O'o collapse that plugged things up that caused the whole process to unfold?
That's a good question. What caused the pressurization of the whole system building up to the thing? It was probably some kind of, well, this is hard to know because you can't pin it down. But clearly there was an obstruction. The normal steady state that was going on between 2008 and 2018, between Summit, Pu'u O'o, was jammed up by something. Maybe a collapse, a local collapse, but we don't know that for sure. But whatever it was, all the indicators show that the whole system was hydraulically just pumped. It was just really gorged. And then something gave to start the whole thing going. Yes? Yeah, oh, wait a minute. Okay, go ahead.
So I've heard that volcanic eruptions can cause actually a cooling effect on the climate. Is this true for this eruption too?
Yes, large volcanic eruptions can cause a cooling effect. That's been well documented in very large explosive eruptions. These are not hugely explosive, okay, on a scale of things. It's not like a big Yellowstone explosive eruption or big eruption of other explosive volcanoes that actually cause global temperature drops. And yeah, no, that's true. But this one, my guess is not going to have any kind of a major effect on the climate. Pardon me.
Were you able to gauge the changes in the size of the magma chamber preceding this eruption, and what volume of the magma chamber was drained out during these eruptions?
That's a great question. I don't have an answer to that because I haven't studied this directly. This is information I've got. But you can be sure that the people at HVO are going to be doing very detailed studies of what they think the current configuration of the magma reservoir is versus pre-2018. Now, you know, it's not a precise science. You know, we have to keep in mind that, you know, when I show that picture of a sphere filled with magma, that ain't the way it is, all right? What it is a plexus of dikes and sills and with solid rock. But the whole thing has a physical property of seismic velocities much, much lower than solid rock. So everything is modeled. And so this is going to get into a very interesting question of modeling, how precise the data are. And the data for this eruption is going to be fantastic. And you can be sure that the geophysicists are going to model the heck out of it. They say, okay, now, you know, the post-2018 configuration of the reservoir at Kilauea is now this. And then someone will say, well, yeah, but you haven't considered that, and so on. I say, yes, ma'am.
So should houses have been built in that area?
Wonderful question.
What's going on now with it?
Okay. Well, right now, as you might gather, there's incredible rebuilding starting very slowly. First of all, they have to rebuild the roads for access again. A lot of houses were destroyed, but a lot of houses weren't destroyed, but you can't get to your house anymore because it's all covered by lava. So the county of Hawaii and the state of Hawaii is making some really tough decisions on how much infrastructure to rebuild, and also 900 telephone poles, or you know, all kinds of things have happened because of the eruption. But the process is just starting. So, but what's going to happen? Why they were, you know, I mean, the people do is, well, these are dangerous areas, you know. And in 1955, an eruption that destroyed houses there. In 1960, there was an eruption there that destroyed houses there. And why did the government officials allow people to build in those areas? That's a great question. And part of the answer is that the USGS HVO has done a very nice lava flow hazards map for the whole island, showing which parts of the island are the most vulnerable to lava flows. And as you might expect, the Puna district that I just showed you here, you're on the East Rift Zone, you're down slope from the East Rift Zone. Gravity usually flows downhill, right? So those areas are rated hazard zones 1 and 2 on a scale of 9 for the Big Island. And the insurance companies, when that hazard map first came out, said, we're not going to insure people in hazard zones 1 and 2 anymore. Because, you know, that's crazy. Or why would we do that? We'd lose money. But the state of Hawaii then came in and said, oh, no, you can't do that. We want to encourage economic development on the Big Island. And so they actually overruled. The insurance company said, you will make insurance available to these people. You can set the rates as high as you want. And the rates are very high. You can get lava flow insurance through Lloyd's of London and a few other places, but not too many local companies. And, boy, I'm sorry, that very few people pay lava flow, get lava flow insurance. And yet, the problem is, this part of the island, because of its hazard zonation and so forth, is the most affordable. So if you wanted to buy a house, no, it really is a catch-22. So most of the houses that were destroyed are not mansions, okay? I mean, some are substantial, to be sure, but a lot of them are pretty modest buildings and dwellings. Because people say, hey, I can get a lot in that subdivision for 1/4 of the cost that I can in the city of Hilo. And so it's a problem. That puts HVO and the USGS in a very challenging position. It is our job to warn people about hazards and the dangers, and we do the best we can. But you can't convince all of the people and the officials, of the, ideally you don't want to build anything there. You want to keep it a whole big national park, probably. But anyway, yes. Oh, Susan.
I just wanted to make a comment that at the time that we were there last year when this was going on, and they were saying there were something like 780 structures had been destroyed, and yet the official count is 700. And I kept asking, why is there a difference between the official count of 700 and then we're seeing on the TV or on the radio or on the newspaper as 750 or 80 or whatever. Well, it turns out they weren't counting any building that was not built with permit. So the ones that they are reporting as destroyed were built with permit, and there were a lot more destroyed that were built without permit.
Yes.
I had a question. It was apparent prospectively that this thing was getting more and more active.
Mm-hmm.
So what have we learned about, predictions or?
Well, okay.
or
On that-
That may be a whole lecture in itself.
Well, yeah, that is. And as it turns out, Kilauea is probably one of the best studied volcanoes in the world. And even there, we can't predict precisely when an eruption is going to take place.
Were scientists,
Oh, scientists are trying to do this all the time.
But I mean, where they had a lottery for, guessing when it was going to blow or.
Oh, no, there were certainly suspicions.
Just,
I mean, the fact that the whole system was ramping up, if you were on the staff there, if I was on the staff there, I said, well, hey guys, something's going to happen. This can't keep up at this rate. Something's going to give. But the state of the art in volcanology is that we cannot predict precisely the day when something is going to finally give and break. So, but
I understand
yeah.
that, but it's just sort of like, since it's been so well studied, we must be a little farther along in understanding this.
Well, we do better at Kilauea than we do probably any other volcano in the world. And I'll say that, and I'll stand on that statement. But that still means we may never get there. Nature is inherently complicated, and
And will it be volcano dependent? In other words, this volcano has this particular kind of behavior versus like, everybody's hysterical about Yellowstone.
yeah. Okay.
We hear it in the newspaper here. Oh, Yellowstone risen.
Right. No. Well, actually, the I can say this with a very bold-faced statement. Each volcano behaves differently. You cannot say volcano A is going to behave exactly like volcano B. That ain't going to happen. Now, what we can say is that volcanoes A and B are generally similar in that they do this and that, but no volcano is identical to another one. Now, when you talk about Yellowstone, that's a totally different category of volcano. I mean, you're talking about caldera systems and explosive eruption, a very, very different kind of a beast. So they're making analogies or comparisons from Kilauea to Yellowstone. It's just, no one in his right mind would do it, really. So, yes?
You showed two videos. One was, is it lava?
Yeah.
Flowing very
Slowly, yeah.
Then you showed some jetting out into the ocean. Is that the same material?
That is compositionally the same material.
But it's protected, it's kept fluid, it's kept hot in a lava.
Right. Lava tubes and lava channels, or lava tubes in particular, if it's totally isolated, is very well thermally insulated. In fact, I've been involved with making measurements and velocities in lava tubes, lava flowing through, and it is amazing the temperature drop of the lava after flowing, let's say, for 5 miles in a tube is like maybe 5 degrees or something. I mean, it's so well insulated, so it can go for 10 miles or so and come out still pretty much at 2,000 degrees Fahrenheit.
How do you measure that velocity? Ultrasonically?
Well, actually, you can just see it there, and and also the as I showed in one slide, the drone measurements.
Yes.
By making repeated measurements and then modeling that data, you can actually measure velocity of point A to point B pretty well. Yeah.
Why don't you describe how you would have people standing in one sky?
Oh.
Drop in a piece of wood, and then someone downstream tells when it explodes.
Okay.
Something really, really complicated.
Okay, now wait a minute. Okay.
Yeah.
First of all,
Complicated nowadays.
I want to make a disclaimer here that I did not plant questions through my wife here, okay? I mean, she's thinking this stuff up, but okay. But when I worked at the Volcano Observatory in the early 70s, the techniques we used were a lot more primitive than what I'm talking about here, what's currently being used. So, but we had a very simple way of measuring the velocity of flowing lava in a lava tube. As you follow along the lava tube system, there are small openings that we call skylights, where it's locally collapsed, and actually you can look through this thing and see the lava flowing beneath you. We can get a pyrometer, measure the temperature of that lava with a pyrometer, but it's flowing fast enough, you really cannot make an estimate. Oh God, that's fast, but what is it? Well, following along on a lava tube system and having different openings, we would have people stationed at different openings. And the person upslope would throw in a branch, a chunk of wood on top, throw it into the hole, and then people down below would hit their stopwatch. And then since wood does not burn in a lava tube, there's no oxygen, when it flows by the next opening, it flares up, and the guy there hits his stopwatch, and then it goes underneath, and it doesn't burn up again. I mean, we're talking wood in 2,000 degrees Fahrenheit. And so we were actually getting measurements of flow rate through the lava tube. It's not Einsteinian by any means, but it's... Yes?
So I'm thinking about the initiation of this particular event. You have a hydraulic system, which is all coupled, and it's being fed from the mantle down below the lava chamber.
Correct.
And I guess I would assume that there's a constant pressure,
flow rate,
pressure, first of all, which is pressurizing this whole hydraulic system until something breaks.
Right.
And in this case, a plug of the
piston, yeah.
Right.
Yeah, right. No, that's right. In fact, one of the interesting things that we can do is actually, depending on what we see erupted, we can make some guesses as to what the mantle input is from what we see come out ultimately. I mean, if it never erupted, the whole thing would just puff up and puff up and puff up, but we don't see that. So there's some kind of a quasi-steady state, and it fluctuates. And in recent decades, we've been able to actually publish papers saying that during this particular period of time, the mantle inflow was higher than before, and so on. With error bars, of course, it's not that quantitative. Yes?
How quickly does the temperature drop in one of those flows when it stops?
It stops in water or stops in air?
No, when there's no more lava coming down in the inside of it. How quick, I mean, the top is cool.
Oh, yeah.
Speaking.
Yeah.
But to go all the way through 10 feet or so, and how
well, okay, first of all, it depends on the flow. In an flow, where it's already rubbly and chunky, if that stops, that's going to cool more quickly than a fluid flow with a molten core. And doing field work there, I've collected samples using a geologic pick, dipping it into the molten stream and pulling it out.
You get that picture of that.
Yeah, that's right, exactly. And then you can put that down, and I learned very quickly, you don't put that sample in your sample bag very soon, because it'll burn up the sample bag canvas. So you learn, and you say, okay, I better wait 15 minutes, and then you see how, touch it lightly. But lava does cool fairly quickly, and in fact, you can actually walk on an active lava flow after the top part is, let's say, consolidated to a few inches. Actually, I've actually walked on lava flows and leaving my boot print sinking into the solid part, but without going through. But you're right, but it's No, she knows that. She knows that. Yes, John.
Two comments, or questions. You commented about andesite coming out of
Yeah.
this thing. Where on earth did that come from? How did it get there?
That's very interesting.
And the second one, top of Mauna Kea is where they had always been measuring the CO2. Was there any indication, hiccup on the gauges up there as far as CO2, or is all the winds going the other way?
To answer your second question first, I'm sure, not the Mauna Kea, but the Mauna Loa Observatory, which measures the CO2, has probably picked up perturbations in their normal global concentrations. But I'm sure we'll probably see papers on that, but I don't know that information right now. Be little blips on the curve. But then your first question about why andesite, which is a volcanic rock that's very compositionally different than the Hawaiian basalt. And the explanation for that is that a lot of the magma that moves from the summit reservoir into the rift zone doesn't get erupted. So there are pockets of stored old magma in the rift zone that are fractionating, that are crystallizing, and that are changing composition toward more felsic rocks. And that's what in fact, the whole chemical story in this thing's gonna be interesting, because the first stuff erupted was not what they thought. It was compositionally somewhat different than what Pu'u O'o was putting out and the Summit Lava Lake was putting out. So that first stuff erupted in the first 2 weeks was stored magma in the rift zone that came out first, and then 2 weeks later, the hotter, more fluid stuff broke through, and that's when we had the really vigorous eruptions.
So you're basically saying that in John's hydraulically complex structure down there, you're getting fractionation and
Exactly.
and
Exactly.
all the normal processes.
Exactly. In fact, I mentioned the geothermal company, in their exploratory drilling a few years ago, they were putting more drill holes in for production wells. And they encountered, in the course of drilling, some molten dacite, which is even more different than the Hawaiian basalt. So they actually, with a drill hole, encountered one of these pockets. Yes, ma'am.
Do you know anything about the telescope that they are?
Oh, that's an. Okay. Okay. That's a very complicated situation, and what she's referring to is this 30-meter telescope that's going to be this new one that's going to be built on the summit of Mauna Kea, and it's been highly. Pardon?
Maybe.
Well, I mean, that was the original plan. But this project's been on the books for years. There've been all kinds of environmental impact studies done and this and that, so on and so forth. Then finally, the state of Hawaii finally signed off on it with threats of lawsuits from the protest groups, mainly the native Hawaiian people who say that building this big new telescope is going to decimate the landscape, and you're going to destroy our heritage, and so on and so forth. And what you're referring to is that all these protests that have been going on up until the state gave approval, it was sort of largely non-dramatic. It was just sort of going on in the courts and meetings and so forth. But once the state gave its approval, then the protest groups came out and blocked the saddle road and stopped traffic, and police got involved, and violence took place. So right now, it's still a chaotic situation. There can be lawsuits. There's still people saying, yes, it should or should not be built. I don't know where it's going to go.
100 of them jobs and see what happens.
Well, maybe I shouldn't tell this story, but I will. A lot of it is not what you think on the surface. And I draw upon my experience when I worked at HVO in the early 70s. In that research drill hole that was put down inside the national park, first of all. This was very rare. And it was put, the principal investigator was a professor from the Colorado School of Mines. And he got this big grant from the National Science Foundation to put in this drill hole to explore a geothermal system near the magma reservoir. It was the ideal place to do it. So I was involved with that whole drilling process and everything. But before the drilling could get started, this guy had the research grant. You know, he had the drilling companies lined up and the whole deal. A group called the Congress of Hawaiian People raised a huge protest threatening to block the road with their own bodies, all kinds of publicity about you're raping Madame Pele, the goddess of volcanoes, with this drill hole, and all kinds of stuff. And of course, being on the staff of the observatory, I and my colleagues had to go to all these public meetings and so forth and defend the scientific basis for this drill hole. But then, and to make this long story very short, is that the whole thing got settled when some of the Hawaiians who were protesting got an offer from the principal investigator, the guy from Colorado School, right? Look, I'll offer you some jobs. And they called the thing off. So, whatever. So, and I, as a young guy at that time, was very disillusioned by that whole thing. Was, oh my God, you know, what do I believe here? And I've probably taken too much time with people.
One more question for Bob?
I have one that's deep and maybe unanswerable. You've been working on Hawaii for a long time. How do you visualize the hot spot and what caused it? And if there's not an answer, you can say it.
You know, I can't really say anything about that. You know, the hotspot idea, although is accepted by most volcanologists, there are some very strong opponents of it who just don't believe that they exist. And because they cite other alternative hypotheses to explain why you get volcanism in one place for millions of years. I personally think hotspots are real. There are not as many as some people have proposed. Some people advocate almost any volcanic center as a hotspot. So they have hundreds of hotspots around the Earth, which I totally disagree with. I personally think that the Hawaiian hotspot is very well documented, and it's almost impossible to explain by any other hypothesis other than a plate coming over a relatively fixed spot. And I say relatively because now data is showing that the spot can move, but moving slower relative to the plate motion, so you still can get that big bend in the Hawaiian shape. And the prevailing theory is still on that, is that bend probably reflects a plate tectonics motion change about 42 million years ago.
All right, couple of things here.